Flow Design team is based in Split, Croatia. Our team members are enrolled in undergraduate and graduate programs at University of Split, Faculty of Electrical Engineering, Mechanical Engineering and Naval Architecture, or as we call it, FESB. This is our first year in competition. First, let's introduce the competition team.
My name is Petra and I'm team captain at Flow Design team. I'm a team member for 1 year. I'm currently Mechanical Engineering Senior at FESB. My field task is Mission Commander.
My name is Mate. I'm electronical engineering student and I have been on this project for 2 years. My task was wiring the aircraft system as well as developing a propulsion system, and my role on the field is monitoring the mission planner and the autonomous flight.
My name is Mirko. I'm a student of mechanical engineering on my 3rd year of undergraduate studies. I joined Flow Design to help them develop flight and communication systems. On the flight line, I will be controlling the ground control station.
My name is Vincenzo and I'm a software engineer student. I've been on this project for 1 year and my tasks were developing an interoperability communication system as well as an image recognition system. I'll be assuming the role of mission commander for communications and autopilot in the field.
My name is Karl. I'm mechanical engineering graduate and I've been in team for 2 years. As safety pilot, my duty is to intervene the flight in case of emergency.
My name is Goran and for this competition I'm the safety pilot for the Flow Design team.
My name is Branko Klarin. I'm a professor at FESB, University of Split, on courses Fluid Mechanics, Aerotechnics and Innovation in Techniques. I support and advise a student group, and I will follow this group at the competition.
Our unmanned aerial system, Vector VX3, is divided in 3 main subsystems: mechanical, software and electrical. Electrical is subsequently divided in propulsion and wiring and flight communications respectively. As our development team consists of only 4 members, each person oversees one part of our aircraft. As the development team chose flying wing, blended wing body configuration, Petra tried to find the optimal design while having in mind characteristics needed: flight time, flight distance and maximum takeoff weight. The design process was iterative, which means that we were changing geometry, doing finite elements analysis, computational fluid dynamics analysis, combined with air tunnel test results to improve and optimize before starting production. In collaboration with Rimac Automobili, we have built 5 prototypes made of fiberglass and carbon-reinforced polymer using sandwich structures. To reduce possible development and mission risks, electronics team members Mate and Mirko opted to use Pixhawk 2.1 flight controller, which is the leading open-source autopilot system. It provides fully autonomous capabilities to the unmanned aerial system, but also offers pilot manual override at any time. Pixhawk software is based on open-source ArduPilot and gives us the option to execute return to launch directive if the primary radio control is lost and cannot be re-established. Other than that, the Pixhawk autopilot is a small and lightweight piece of airborne hardware with low power consumption and no special cooling requirements. 2 separate communication channels between the aircraft and ground control station are implemented. First one, the 433 MHz DragonLink V3 is used as a telemetry connection between the mission planner and the flight controller. It is also used as the RC control by a safety pilot in manual mode. Second one, a dual-band 2.4 and 5 GHz Ubiquiti AirMax link, which consists of the rocket base station and the bullet transceiver in the UAS, is used as an imagery data link such as FPV and photo-video stream. To guarantee adequate range, both the rocket and the bullet are attached to the 11 dB gain omnidirectional antenna. The ground control station is used to control the UAS via 3 separate stations: the mission planner station, the payload operator station, and the mission commander station. This is done by setting waypoints and target altitudes and changing autopilot modes. To maximize endurance, Electronics team came up with the idea of designing the lithium-ion battery pack 18650 design. Its energy density is approximately 40% higher compared to an off-the-shelf lithium polymer pack. The drawback of these batteries is low discharge rate, which is compensated by a power supply balancing unit, running several battery packs in parallel. In case of high discharge rate operations, such as ascending, the pack delivers necessary power output from all resources. For cruise mode, it can balance power consumptions and longevity. This feature also allows maximum usability of the cargo bay and aids in trim settings, since it can be spatially distributed within the bay as needed. Because of budget constraints, it wasn't possible to implement this technical solution. At the competition, we will use standard lithium polymer batteries. Our software engineer Vincenzo developed Vector's imaging recognition system. It is composed of Raspberry Pi 3B Plus onboard computer and GoPro Hero 5 camera. We considered other options, but budget constraints and availability in region pushed us towards Raspberry and GoPro. Also, they are well documented, so we could access any information needed. The pre-programmed mode, which will be controlled over a Python library, provides a maximum of 94.4 degrees on the vertical axis, 122.6 degrees on the horizontal axis, and 149.2 degrees for the diagonal field of view, which should be more than enough for the mission. Captured photographs are transferred via the application programming interface to the onboard computer. For establishing a connection between the camera and the Raspberry Pi, general-purpose input-output pins are used. At the competition, we will attempt 3 missions: autonomous flight, obstacle avoidance, and object detection, classification and localization. To prove the readiness for completing the mission, several tests were conducted. We tested individual components, subsystems, and eventually the aircraft to ensure everything works as it should. In the beginning, we tested preliminary design using CFD simulations and air tunnel. We decided to build smaller scale prototype and test it in the field before starting full-size prototype production. The smaller prototype VX1 showed us what we must change, for example, flaperons and winglets. We also tested various materials, and in the end, we decided to use sandwich structures made of carbon fiber and fiberglass reinforced polymer. The structure is rigid, lightweight, and resistant to impacts. Electrical components were tested separately to see if they matched their specifications. After passing the tests, component was used to build a subsystem. Before placing all the components in the aircraft, subsystems were tested in lab environment to assure that they can work together in the same subsystem. Pixhawk 2.1 Cube autopilot was configured for full integration with our in-house aircraft to provide optimal performance in terms of flight plan accuracy. We also secured communication with interop server and tested it by installing a virtual machine of the server from GitHub. Also developed a parser for JSON messages. The telemetry was tested at a minimum rate of 1 Hz to the interop server. Raspberry Pi 3B Plus is configured to handle all the communications to and from the UAS. Audiovisual inputs are configured to work with Raspberry Pi and Bullet Rocket data link as well as telemetry link. For each safety pilot, we conducted 13 flights with VX3, of which 10 were autonomous flights. Statistics showed that the average time while airborne was 70%. At first, we had problems with autonomous takeoff because of our launch system, but eventually managed to solve the issue. Autonomous landing was successful in 90% of the cases. As stated earlier, we are using PixHawk 2.1 with autopilot interface. While in an autonomous flight mode, the aircraft passed the sequence of minimum 3 and maximum 10 waypoints per flight. Using telemetry data obtained, we calculated the waypoint accuracy at 82%. Similar to waypoint accuracy tests, telemetry data and ground control data were used to determine if aircraft managed to avoid stationary obstacles. It was tested to 50 obstacles altogether, with number of obstacles avoided at 32. Although only 64%, the number of avoidances is getting bigger by each attempt, so with first results eliminated, it is close to 75%. We implemented a custom neural network based on OpenCV library for ODCL and tuned to detect alphanumeric objects and human figures. The system was tested against video obtained during one of the manual test flights. After some fine-tuning of the algorithm and camera position, we are able to detect, identify, and locate objects at altitude above 100 feet. Percentage of false hits drops, while detection, classification, and localization matching improve. To test object localization, we conducted a field test. Object GPS was recorded using locators and afterwards compared to both telemetry and GoPro geotagging results. After repeating the test several times, average location error was calculated at 17%. Of 10 autonomous flights, we completed 6 full mission tests. The system is fully capable of completing the entire mission. Any flaws the test exposed were successfully eliminated till the next flight. It mainly included software and electronics fine-tuning, but also team communication and organization. All flight tests were treated as we were at the competition, so we provided sufficient coverage. Timeline. At 5 of 6 missions, we were able to complete all tasks stated in timeline section. We are very confident in this part of the mission. Autonomous flight. In 6 full mission attempts, all parts of this mission were covered and executed as expected. We are highly confident in completing autonomous flight mission. Obstacle avoidance. In 6 full mission attempts, we tried to execute stationary obstacle avoidance. 4 of them were at success rate of 70% and 2 of them at 80%. We are highly confident in completing this mission. Object detection, classification, and localization. In 6 full attempts of over 100 targets, average result was close to 80%. We are highly confident in completing this mission. Operational excellence. As a trained team, we are highly confident that we will operate the mission professionally and safely. Our full mission tests and average is 100%. We are very confident in this part of the mission.